it's a great pleasure to see you all back after this super long break that I guess was pretty much the longest break that we ever took. But well, life started to come back to all of us, and hopefully it's gonna go like this. But I suppose most of you haven't forgotten the rules, but I'm still gonna go over them. So the idea is we're gonna have a talk by our speaker, who's gonna be talking for like roughly 50 minutes, and then we're gonna have like 10 minutes of recorded questions. So those are gonna appear on YouTube. If you have some more controversial or complicated questions, you can save them for after, when we stay around and talk for another 30 minutes or so. So I suppose one thing that we have all learned over the last years is, to stay on mute all the time, so that you can hear the speaker, that sort of stuff. Well, I guess everybody knows it, right? So I guess I'm gonna just pass it over to Kira, who's gonna be introducing our speaker today.
Great, thanks. So we're very excited to have Andrew Wagenmaker here today. Andrew is a fourth-year PhD student in computer science at the University of Washington, working with Kevin Jamieson. His research interests are in active learning, reinforcement learning, control theory, and he's done some awesome work in these areas. And he's currently supported by an NSF Graduate Research Fellowship. So we're very excited to hear about this latest work. So if you want to start sharing, and then over to you.
Yeah, thank you, Kira, for the introduction and the invitation to present again here. Can everyone see my screen? Okay, cool. Yeah, so today I'm going to be talking about our paper, First Order Regret in Reinforcement Learning with Linear Function Approximation, a Robust Estimation Approach. This is a joint work with Yifang, it's another student at UW, Max Simchowitz is at MIT, and then Simon Du and Kevin Jamieson, my advisor. Okay, so to sort of like motivate the problem a little bit, in a lot of practical RL, real world RL settings, you can have rewards that are sparse and hard to reach. And so these sort of are two examples. These are both Atari games, Montezuma's Revenge and Pitfall, which are known to have these sort of sparse reward type settings, where you maybe have to take a specific sequence of actions to achieve any reward. And in such settings, to learn efficiently, RL algorithms really need to adapt to the reward level in some sense. And so if you ran a naive algorithm in a setting like this, you might overexplore regions of the state space with small or no reward. And so you can think about, in terms of the exploration bonuses and that sort of thing you might give to an algorithm to induce exploration, it's going to perhaps explore too much, give too much bonus in regions of the space where there is actually no reward. Instead, we ought to, in some sense, adjust the exploration level in proportion to the reward signal we receive. So we should be exploring the regions of the state space where we are actually receiving a large amount of reward. And if we do this properly, in some sense, we can then bound the number of mistakes we make in terms of the reward level, right? So if we're exploring in accordance with the reward we're actually receiving, we can maybe bound the number of times we're over-exploring and therefore incurring regret by the reward level we achieve. And ideally, then, this will be reflected in regret bounds which scale with the maximum attainable reward for the problem instance. And these are called first-order regret bounds. So another way, I think, to intuitively think about what's going on here is, say you have a reinforcement learning setting where, due to the stochasticity in the problem and that sort of thing, the actual reward, even the optimal policy can attain, is very small. In a case like that, you wouldn't necessarily, if you sort of make a mistake while you're exploring, you wouldn't necessarily incur that much regret. And so you would maybe hope that your regret bound would scale in some sense with the reward that the optimal policy is actually attaining. And I'll make this all formal in a bit. So this is sort of the first piece of motivation. Can we get regret bounds that scale with the maximal attainable reward? And so on sort of problems with smaller reward, you sort of have regret scaling smaller, and problems with larger reward, you maybe have sort of the worst case guarantees. So the second problem that we're trying to address is that of large state spaces. So of course, the reinforcement learning community has recently been looking at RL with function approximation and these sorts of large state space settings. And so we want to really consider this problem of first order regret in this large state space setting. So in such settings, you can't obviously visit every state, you have to generalize. And so somehow you have to be able to handle these hard to reach rewards, even in settings like this. And so the sort of goal of this work is to obtain a first order style regret bound in MDPs with large state spaces. And what I mean by that is to have regret scaling as square root of v1 star times k, where V1 star is the maximum expected attainable reward. So sort of the expected value, the expected reward, the optimal policy achieves, and K is the number of episodes. And you might have some other polynomial D&H factors and stuff like that, but the main scaling we care about here is, can we get it in terms of this V1 star? And again, this means basically you could, if you have an instance with V1 star very small, this says that essentially your regret is scaling in accordance with this V1 star. So you're getting much better regret. And I want to emphasize this isn't just sort of like a cute theoretical thing. Like going back to the last slide, this is actually something where you're trying to actually come up with better algorithms. So algorithms that take into account the reward level and actually do explore better, not just that get better sort of regret. We're not just trying to prove sort of nicer regret bounds. We're actually trying to get algorithms that perform better in these sorts of settings. So this sort of setting of first order regret, I'm not going to go into a huge amount of detail on sort of all the background, but there's a huge amount of literature out there, and everything from just sort of standard statistical learning to online learning and various types of bandits, where basically the goal is, again, to get regret that scales in some sense with the performance of the optimal policy. So in particular, I'll highlight some of the recent work that's been going on in contextual bandits. So in 2017 at Colt, this was posed as an open problem for contextual bandits if we can attain first order regret bounds. And it was solved then in 2018 with a computationally inefficient algorithm, and only last year in 2021 with a computationally efficient algorithm. So this is still, like, even in the setting, the simpler setting of contextual bandits, this is still a very recent problem that people have been working on in just the last year. In the RL setting, to my knowledge, the only work out there that actually deals with this is the Euler algorithm by Zanet and Brunskell, and this only is restricted to the tabular setting. And so obtaining first order regret in RL with large state spaces has remained an open problem, and as we'll see, there are some like subtle differences in terms of the techniques we need to get this regret. I will also mention, just to contrast this, you can think of these first order regret as a sort of type of instance-dependent regret bound, and I want to contrast this with the gap-dependent regret bounds that you'll also see in the literature. So there's been numerous papers in the last few years where you get regret scaling as like log k, sum over inverse gaps. And this is also problem dependent, but in some sense, what this regret bound quantifies is the total regret needed to solve the problem. Whereas sort of first order regret is, you can think of it as much sort of, it's a much tighter regret bound for small k values. So for small k values, this could still be quite large, while the first order regret captures more of that small k regime and the actual regret you might be incurring in these sorts of problems. And so sort of the what I'll show is we come up with an algorithm, in particular in the setting of linear MDPs, which I'll define in a second. We come up with an algorithm force, which has regret scaling as d cubed h cubed times v1 star times k, plus some additional lower order terms. So we hit this sort of first order regret goal, and our algorithm relies on a novel application of the robust Ketone Estimator to obtain self-normalized bounds which do not exhibit large lower order terms. So we have to come up with some sort of novel technical tools to actually solve this problem in the linear setting, which I'll go into some detail on that. Okay, so before I jump into the preliminaries, any sort of section on any questions on motivation or anything like that?
So I have a...
Sorry, go ahead.
Yeah, I have like a relatively technical question about the differences between these first order bounds and the ones that you cited, because it's, so depending on whether you're talking about losses or rewards, these first order bounds can mean very difficult things, can mean very different things. Mm-hmm. And in my experience, like getting first order bounds with respect to small loss can be a lot harder. So I don't know, like you think about comparing these regimes?
Yeah, I would need to think more.
Is this something that you wanted to discuss later?
Yeah, I haven't thought too much about this, to be honest. I mean, I guess obviously the standard like reinforcement learning setting, we usually think about rewards. And so that was sort of like the motivation for this project, is to sort of, do this in the standard RL setting. I think I would need to think more about what the differences you might have in terms of losses. Although I think, as you'll see, even when you're thinking about rewards, there's a number of technical challenges that arise that was like non-trivial to address. So I would need to think some more, I think, about if you had losses, how that would change things.
Yeah, so my feeling is that having first order bound with respect to the losses, it means that you want to scale with the loss of the best policy, which means that if that loss is good, right, then you want your algorithm to work amazingly well, right? Mm-hmm. which means if the best policy is really good, it's much better than the others, then you want your algorithm to like identify it real quick.
Right.
Whereas this first order reward, it means that you want your algorithm to scale with the best achievable reward. So like the larger the reward is, the bigger your bound is.
Right. I mean, I guess, and yeah, in some sense, though, it's like the natural, I think in some sense it's like the natural scaling you would hope for in these reward settings where like, I mean, even if you just think about the definition of reward, right, you have like, I can just, if you go like the definition of reward, you have like the sum of sort of V1 star minus V1 pi k, right? And so ideally, if V1 star is incredibly small, you would hope that it isn't scaling with like some arbitrary, like some poly DH factor, like that it is actually scaling in some sense with V1 star. Because again, like if you go back to this intuition of like V1 star is the most reward you could ever hope to attain. And so if you just completely screwed up an episode, you should only pay like V1 star in regret. You shouldn't ever pay like more than V1 star. And so if V1 star is really small, you sort of want your regret to account for that. As I guess sort of the intuition we have for this.
It's kind of more close to the gap dependent things that like if like problem is expected to be easier if even the optimal policy cannot collect much reward.
Right.
That
right.
the gap is small. The problem, well, okay, the gap is it's like the gap dependent exactly doing the opposite thing, but it shouldn't, right? Because it like problem altogether is in a way easy because you're not giving up much, while the gap dependent that's talking about something else, right?
Yeah.
Okay, well, a small question, which just, yeah, I think you're gonna say this probably on the next slide, that all this kind of assumes that the smallest total reward that you can ever achieve by any policy is non-negative or zero or something, like you're offsetting things here, because otherwise, like, okay, what was the meaning of this? Like I can shift around things.
Right. Yeah. So we assume, I'll say this on the next slide, but we assume the rewards are bounded in 0 to 1. So you're the like sort of minimal, you always will get at least 0 reward. You can't ever have like negative reward.
Yeah, that's a little bit different than, for example, if you would assume that the total reward can never go, like total expected reward can never go below 0. It's like summing up things and then making an assumption, or, you know, like minuscule assumptions on every reward.
Right.
I don't know, is there any difference between these two?
Well, like, I guess if you could, if we thought about a problem where the reward is actually always 0, then your regret is always 0, because like, it doesn't matter what you do, you always get zero reward.
Well, I guess I'm talking about cases when the reward could be negative, but then you get to some state such that later it's compensated and the total reward is...
I see. Yeah.
And the variance, you know, like because of that could be higher or something.
Right. I think it might, I would need to think more about it. It might work, I think, just by like doing some shifting of a reward. We haven't really thought about though. I mean, again, like the standard RL setting sort of assumes rewards in 0, 1. So we haven't really thought about negative rewards. Yeah, I mean, I guess it would make things weird. Like now your value function is negative in these
we can discuss this at the end of the talk a little bit more. Like, I think it's kind of interesting to think about these cases.
Okay, yeah.
This is a good start. Yeah.
Okay. Cool. So any other questions, or are we good to continue? Okay. So I'll just quickly introduce our setting. So we're going to just be looking at basically standard episodic non-stationary MDPs. So some set of states, some set of actions. H will denote the horizon. P of H is the probability of transitioning from state to state S prime if we take action A in state S. Rewards again are in 0 to 1. We'll assume deterministic for simplicity. And we'll also assume the MDP always starts in state S naught, and then we can sort of like encode the initial initial state distribution in the initial transition. So we're going to assume the transition kernels are unknown. We'll assume the rewards are known, and I'll make a remark on this in the next slide. And then pi, as usual, we'll just denote a policy mapping from states to actions. So again, we're going to be looking in this large state space MDP setting. So in particular, we're going to look at the linear MDP setting. This is a setting considered by Chi-Jin in his paper, Provably Efficient RL with Linear Function Approximation. So it's one of the sort of most common RL formulations with linear structure. So the definition of a linear MDP is basically the following. So for every state and action, there's some known feature vector associated with it, phi of SA, and this lives in a d-dimensional space. And then we'll assume there's h unknown signed measures mu of h over S, such that the probability of transitioning to some state, given that you play action A in state S, is given by the inner product of phi of SA with this measure. So it's essentially all parameterized by this linear feature vector. And then we'll assume some normalization. One difference between R setting and Chi setting is we're not necessarily assuming their rewards are linear. So it could be sort of an arbitrary reward function. We do assume they are known, as I said. If we wanted to assume they are unknown, we could do this, but we would have to add the linearity assumption. So all the results go through if you assume linear and unknown. But I'll just be assuming known and not necessarily linear for now. Okay, value function, sort of standard definition. Q of h pi is just going to denote sort of the Q value function, the expected reward you're going to achieve. Q star and V star are going to denote the optimal value functions, pi star the optimal policy. And we're going to define the value of a policy by V1 pi, which is just sort of the expected reward policy pi will achieve. And one thing to note about linear MVPs in particular is that for any policy pi, there exists some set of weights WH pi such that the Q value function Q of h pi of SA is simply given by the inner product of phi of SA and WH pi. So this holds true for any pi, not just pi star, so it's a pretty strong linearity assumption. But sort of a nice feature of this is that when you're sort of doing your learning in some sense, you can really reduce all the learning to just learning these linear functions. And then finally, I'll just define that regret, standard definition of regret. So basically the regret after k episodes is just sort of V1 star minus V1 pi k, where pi k is the policy you played at episode k. And again, our goal is going to be to obtain a regret bound scaling with V1 star. Some notational things, again, we will use this sort of E of underscore H of SA to sort of denote the next state expectation at step H if you play action A in state S. And we'll use S underscore HK and A underscore HK to sort of denote the state in actions at step H and episode K. Okay, so that's sort of the notation, the setting. Any questions on that? It's essentially, again, the standard linear MVP setting that many other works have considered. Okay, so I'm just going to state now formally our main result. So basically, there exists an algorithm force, which with probability at least 1 minus delta has regret bounded as, again, d cubed h cubed v1 star times k, and then some extra log factors as well as this lower order term. Now, our algorithm is actually force. It sort of in this form is actually computationally inefficient, but we come up with a computationally efficient version of force that has regret scaling as d to the fourth h cubed v1 star times k. So basically, you can make it computationally efficient, but you pay an extra factor of square root d. So it's a bit of a trade-off here, and I think removing that is an open question. And just to quick compare this to some existing works out there. So again, this work by Jin, provably efficient RL, linear function approximation, they get regretted d cubed h to the fourth k in a computationally efficient algorithm. So V1 star is always less than H because we assume the rewards are in 0, 1, which means that our computationally inefficient algorithm in the worst case is no worse than the Chi's algorithm. Zanet has an algorithm that gets regret d squared H to the fourth K, but their algorithm is computationally inefficient. So hitting that sort of d squared rate with a computationally efficient algorithm is still an open problem. Okay, so this is sort of our basic result. So I want to now basically spend the rest of the talk talking about going over the techniques, because I think this is sort of the interesting pieces of this paper in terms of how we can get this first order scaling. So to sort of motivate what we do, I want to sort of look at some of the techniques existing works have used and sort of talk through why these seem to not be sufficient to get first order regret. So I want to talk in particular about two sort of papers. First is this paper of Jin. And essentially their algorithm is a least squares value iteration style algorithm. And so Again, if you recall, I said that in linear MDPs, you can always sort of approximate the Q-value function using a linear function. And so basically what they try to do is at every episode k, they compute this WH, which is essentially this approximation to the Q-value function. And they do this by solving a least squares problem based on sort of the data they've observed. Then they play an action AHK, which is essentially sort of optimizing this Q function plus some bonus term to account for the uncertainty. The details sort of this is not of exactly how their approach works is not like super important. But the thing I want to highlight here is basically that the key inequality they use to get this algorithm to show low regret is this self-normalized martingale vector martingale bound. And this has been sort of commonly used now in linear bandits, going back at least a decade, and now in linear RL in numerous papers. So it's a pretty standard technique. And basically what it is you assume, if you have some sort of vector valued martingale, you assume that you have this like eta tau, the noise is upper bounded absolutely by h. And then if you assume that, then you can show that this term here is upper bounded by roughly h in square root of d. Again, the details of exactly what this bound says is not hugely important, but the important thing to note here is that this is a very much a Hoffian style bound. So it relies on the fact that the noise is absolutely bounded, and then the sort of bound you get on the concentration scales with sort of this absolute bound on the noise. And so it doesn't seem like naively we can necessarily improve on this using this concentration bound, or at least it's not clear how to. However, this is sufficient for getting a poly DH style regret bound. So it still gives a provably efficient regret bound, but it's not clear that you can actually improve on this just like raw H dependence. Now, sort of it's pretty well known, I think, at this point that at least in the tabular setting, to get these refined regret bounds, you want to switch from using a Hoffian style bound, which is again this very worst case bound, which scales with the absolute magnitude of the noise, in this case H, and you want to switch to a Bernstein style bound, which accounts for the variance in the noise, or the variance in the next state value function. And this is what the Euler algorithm, essentially how they get this refined dependence on these problem dependent quantities, as well as other algorithms out there. And so you might ask the natural question is, well, can we just sort of like come up with a Bernstein version of what Shida does and use that to then get this first order scaling? And so it turns out there are actually Bernstein style self-normalized bounds. This one is due to Chaba as well as his collaborators, and this came out, I think, end of 2012. And they show the following bound now. So instead of just giving, you still assume the noise is absolutely bounded by H, but we're also going to assume this bound on the variance of the noise. And what they essentially show is that now the self-normalized term, it scales with the variance of square root of D. But it also does still scale with the absolute magnitude of the noise. And it seems like, as far as we were able to tell, this is not necessarily improvable directly using sort of the standard self-normalized techniques. And so what sort of pushing their argument now is, if we sort of try to do what she does, maybe using this sort of Bernstein style self-normalized bound, we can try the following thing, which is, well, let's sort of again use this least squares value iteration approach. Let's try to solve for these W functions, but let's do this now in a variance dependent way. So say we have these estimates sigma HK of the next state variance. Let's solve this least squares problem that she solves, but now we'll just normalize by the variance in some sense. So it's a weighted least squares problem. And we're going to make the crucial assumption here that the variance is lower bounded by a sigma min. If this doesn't happen, if you don't do this, then you could have, say, variance that would be 0, and this would mess up your problem. So you need to assume some lower bound of the variance. And if you push this through, what you'll see is that using this Bernstein style self-normalized bound, you can get a regret that scales something like square root of D plus H over sigma min plus the sum of the variance. And so this is sort of good in that, like, we're getting now the sum of the variance, which is what we wanted originally. And if all we had was the sum of the variance, this would actually be sufficient to get this first order style regret. Now the issue here is that due to this lower order term in the Bernstein self-normalized bound, you still are paying this 1 over sigma min factor. And if you sort of just recall that this is lower bounded by sigma min squared, then you can lower bound the regret bound we have here by something that scales with poly H times K. And so the point being that because of this lower order term in the Bernstein bound, this sort of magnitude term that still shows up in the Bernstein bound, you can't actually get this pure first order regret. You get this sort of, you end up paying this 1 over sigma min. This cancels with the variance dependence you would hope to attain, and you're still left with this like square root of k style regret. And so this might be a sort of sufficient if you want to just get improved dependence on D and H, but it's not clear that you can use this to obtain first order regret. And in fact, the Chavez paper, which uses this regret bound or this self-normalized bound, they do show that it's sufficient to get improved dependence on D and H, at least for the linear mixture MDP setting. So this is still buying you something, but it's not buying you quite enough due to the lower order Bernstein style term. And so I think the takeaway, if that was sort of too fast, the takeaway from this is that in tabular, we know we can use Bernstein, and we get these like lower order terms, which are truly lower order, and we can then get sort of this variance dependence that we would want. But it seems that in linear, when you apply these self-normalized bound, this lower order term that shows up in the Bernstein is actually too large to attain first order regret. So it seems that we need something actually better than Bernstein to get the first order regret scaling we're hoping to get. And so that's where sort of we introduce the use of Ketone estimation in RL. Any questions on all of that before I jump into Ketone? Okay, so I'm gonna sort of now define the Ketone estimator and show how sort of we build up to use it to achieve the regret bound. Let me check. I'm doing it time. Okay. So the Ketone estimator, this is something that's been around for a while now. I think going back to like 2012 is when it was proposed, I believe. But it's really something coming more out of the robust estimation, the robust statistics literature. And the Ketone estimator is defined as the following. Let's define some function f cat of z. And say we have some random variables xt. Our Ketone estimator is going to be the unique root of this function of f cat of z. So whatever z makes this 0. And this phi sort of depends on this logarithmic function. And essentially, in effect, what this does is it reduces the effects of the tails. And you can show, it's a pretty clever argument, you can show that it has some really nice properties. So in particular, what Ketone shows is that if you have some random variables, x1 to xt, let's say there's a mean mu and their IID, and they have variance sigma squared, the Ketone estimator with parameter, so the Ketone estimator has this tunable parameter alpha. So with proper choice of alpha, it'll produce an estimate mu hat such that mu hat minus mu is upper bounded. The deviation is upper bounded by sigma squared times log 1 over delta over t quantity square root. And so we can contrast this with what you would get for Bernstein. If you tried to apply, so first off, this doesn't necessarily assume they're sub-Gaussian. It just assumes they have bounded variance. All you need is bounded variance to get this scaling. And so if you were to apply Bernstein to bounded random variables, you're going to get this extra lower order term. Say xi is absolutely bounded by some value gamma, then you're going to get a lower order term of gamma over t. That's what Bernstein is going to give you. Hofstein will just give you sort of gamma times log 1 over delta over t. But with Ketone, we can get purely a variance scaling. We don't get any sort of dependence on the absolute magnitude of the noise. And as we'll see, this, again, if going back, you can maybe already see where this is going back to these previous issues that we had with these self-normalized bounds. The issue was that we were getting these sort of absolute magnitude terms still showing up. But Ketone sort of gives us concentration without that absolute magnitude term showing up. And so we're going to be able to push this through to get the proper dependence we would hope for, and ultimately get this first order style regret bound. But there's several issues here. So again, if we recall that, Chava, you have your hand raised?
Yeah, I'm just wondering about like, help me understand this a little bit better. So it's robust estimation, whatnot, but one example when this dependent on a scale shows up in Bernstein's in this mean estimation problems is if you have like this bi-valued random variable. So the random variable takes on values of 0 and b, right? Mm-hmm. And then like you see zeros because the probability of seeing zeros is really high, but the expectation is somewhere in between. And like how does this like, so usually you use this example to show that the dependence on B is necessary in Bernstein's inequality, and now we don't have that. So can you shed some light on how does this happen?
Yeah, I mean, I think so. The intuition is that basically these logarithmic functions sort of smooth out the tails. So I guess one thing I'll mention is it depends on, you actually need to know the value of the variance. This sort of optimal scaling, or this optimal tuning parameter alpha, depends on the variance. And if you don't know, I believe if you don't know the variance, you can't necessarily actually get this to work. So it just sort of assumes you know the variance. And so I think that's one thing. But and I think that intuitively what's going on is that it sort of smooths out the tail. So if you have like a heavy tail distribution, this logarithmic function smooths out the tails so that you sort of only see the effects around the mean a bit more. In terms of like the actual analysis to get the Ketone estimator, it uses basically a really like, I don't have a slide on here, so I can't just show it there, but basically it uses a really like nice trick when you sort of like try to write out the basically like the estimator you would, or basically when you try to write out like Markov's inequality and then you do the exponential like in a Chernoff bound, you get some nice cancellations with say log factors, and you actually have like sort of a cancel. You find that you actually don't get this dependence on the variance. So I don't know. I don't have a great intuition. That maybe is not quite what you're looking for. I don't have a great intuition beyond this of sort of like how this is able to sort of like do it. Beyond that, it sort of is like smoothing out the tails.
I guess your answer of that, you need to know the variance, is kind of pretty good, because now I'm thinking about this example, and yeah, in this example, the what's critical is that this, like, you only observe the zeros and you don't observe the big value. So if you have no prior information about how big that value is, like, what can you do? Like, you either need to include that prior information, or like you're doomed. Like, you can't get a confidence interval for this, right? But if you have an idea about how big the variance is, that also confine things. And also, I guess a related thing is that this only works at a fixed confidence level, right? So this is not uniform for...
Right, yeah. Again, it's sort of like median and mean in that regard. It takes as input, in some sense, a delta.
Right.
And your estimate actually depends on that delta. Yeah.
Okay. All right. Okay. Good.
Yeah, I think that's really good intuition, what you said there, Java. What's going on here?
You said it. Okay, thanks.
Okay, other questions on Ketone before I move on? Okay, so now thinking about how to apply this to RL, there's several issues. So in particular, we might think about sort of doing what Chi does, which is solving this least squares problem. And instead of solving the least squares problem, we know that basically the least squares problem is simply a sample mean, right? So like this WH vector, you can just think about it as a mean of all of these terms. And so you can think about Ketone takes as input a bunch of data and it sort of computes a sample mean. We can think about computing WH by applying Ketone to take the sample mean of the data given by these factors. But there's issues with this. In particular, first off, this is centered on vector value, not scalar value, right? So Ketone assumes the data is scalar valued. We really want to get this vector estimate. So somehow we need to come up with a Ketone that achieves this like vector value estimation. But the bigger issues here is that our data is highly correlated. So not only does this have sort of this like martingale structure, but it actually, this lambda HK, which is our covariance, actually depends on all the K. And so this isn't actually even like a martingale. It has sort of like, everything is correlated with everything else essentially. And so you have to find a way to sort of handle all these like correlations with the Ketone estimator. And this hasn't been, neither of these are things that have actually been addressed to our knowledge in the literature. So in the first, to the first point, I want to sort of moving to vector Ketone. Let's just consider some general regression setting as an example. We'll have some ft minus 1 measurable vectors phi t, and assume we get some observations yt, which is just the inner product of phi t and some theta plus eta t. And we assume we actually assume something slightly stronger than bounded variance of eta t. We assume that yt has sort of like bounded squared expected square. Now we can think about applying the Ketone estimator to the data v transpose phi t yt sigma t squared. Now this, for a given v, this is actually a scalar. So we can just apply Ketone to this directly. Furthermore, this doesn't have all of the sort of correlations that I just brought up in the last slide. This is actually just a martingale type sequence. And so there is actually a martingale version of Ketone out there. And so we can actually just apply this martingale Ketone directly to this data. And we see that with the proper choice of alpha, I'm using sort of cat v to denote the Ketone estimate, we can get an estimate of this quantity here. V transpose sigma t times theta, where sigma t is the sort of like variance normalized covariance. And so this is starting to look like now what we might hope for, because for a given v, we can compute a Ketone estimate of this vector value data. And well, it's not quite the estimate of theta in a particular direction v, but it's getting it's getting towards that a bit. But to actually get the right estimate in terms of theta, what we'd want is we want to choose v equal to t sigma t to the -1 of u. And then if you plug that v back into here, you get that this is equal to u transpose theta. Yes, Chavi, you have another question?
Oh, I'm just going to read out Akshay's question, which is, I guess you'll answer that sooner or later, whether the sigma t's are known, like, are we gonna know?
Yeah, so we can assume in this setting here, just the sort of idealized regression setting, assume sigma t is known. When we actually apply this to RL, we actually have to compute sigma t. But I can get into that a bit more when I talk about applying this to RL. But for now, just assume sigma t is known. Okay, so but the issue here is like what we'd want is we want to choose v to be equal to big sigma t to the -1 times u. And if we did that, then we're going to get a cancellation here. And what we have left is simply that sort of it's like a u transpose theta, which would be saying that essentially we're now just estimating theta in direction u. Now the issue with this again is that as soon as you choose v to be this value, now you introduce all these extra correlations because sigma t depends on all the past data. And so as soon as you sort of plug it into the Ketone estimate, you lose this martingale structure completely. And so to tackle this, we basically propose a uniform style Ketone bound. And we do this by developing a perturbation bound on Ketone estimation. So we basically show that you can prove a perturbation bound on sort of the Ketone estimator. And then we can use this to we can apply a covering argument to show that you get sort of a uniform cover over all your data in some sense. And so in particular, let's think about forming an epsilon net of all PSD matrices. In particular, that would include this sigma t, this random matrix that's correlated with our data. And we can apply sort of Ketone to every point in this epsilon net. And then we can just show using our perturbation bound that the bound for Ketone will hold for all PSD matrices simultaneously. And so this allows us to handle these correlations in our data. And basically, we can show then, given this, that let's now run the Ketone estimator on this data. Xt equals v transpose sigma t lambda t to the -1. Lambda t is just a normalized covariance. Phi t yt over sigma t squared. Again, this is not a martingale because of all the correlations within sigma t. But using this uniform covering result, we can then show that for all v simultaneously, with probability at least 1 minus delta, our Ketone estimator in direction v estimates v transpose theta up to this scaling. And I'll talk in a little bit maybe about sort of what this scaling means, but essentially you can think of this as this is sort of the error, the variance term essentially, and you're not paying anywhere for any sort of like magnitude of the noise. So you're playing purely for like a variance term now. But essentially what this says is we've been able to sort of take this Ketone, which is just simply applied to IID scalar data, and now we have a vector Ketone that applies to like highly correlated data. And so we can now think about actually applying this in the RL setting. But we want to take this actually one step further. This is sort of great if you have a fixed v, but you really would want to actually come up with like a theta hat, right? Like we really would want to come up with a vector parameterization. And currently all that we have is we have these Ketone functions that are sort of like, if we care about a particular direction, we can estimate that direction, but we don't have actually a nice representation of our estimator. And so what we can do is we show that you can actually derive, using the Ketone estimator, you can derive a theta hat such that in any direction v transpose theta hat minus v transpose theta scales sort of as the error of the Ketone estimator. And so basically, the key idea behind this is because we assume our underlying data is linear, you can sort of show that if you're approximating the underlying data well with the Ketone estimator, then there has to exist a linear approximation to your Ketone estimators. And this will be really handy when we go to RL, because now we have sort of this lower dimensional representation of this robust estimator. Okay, and so let's just go back now to comparing this to the sort of like standard self-normalized bounds. So again, in this regression setting, if we assume that the noise is upper bounded by gamma now, our estimator will give a variance sensitive bound that holds for all v simultaneously, such that you have v transpose theta hat minus theta is upper bounded again by this term I just showed. The key thing is you get a logarithmic dependence on gamma here, but that's it. You don't get any sort of like extra scaling in gamma. Whereas if you applied the self-normalized bounds I showed previously, either of them, you're going to get a scaling directly in gamma, which is what you see here. The other thing to note here is that this lambda t matrix depends on the variance. So you actually, even though there's no sort of variance directly showing up in the expression I have here, it's all sort of hidden in this lambda t. So you are still getting this like variance dependent estimator. Okay, so that's sort of what we do with Ketone. Any questions on that before I move into its application now to how we're going to apply this to RL? Yeah.
So there were some questions in the chat, and I'm just like on their behalf, I'm going to ask, like, what's the meaning of the weakly inequalities?
Oh, yeah. Basically just up to absolute constants, and then I'm hiding maybe some like log d, and also like log, well, here I'm not hiding log 1 over delta, but I think previously I was hiding a log 1 over delta. Maybe I wasn't. Yeah, it's hiding absolute constants and log terms, but there's no other sort of term that's hiding.
All the d dependencies are shown.
Yeah, there's like a log d too, but all the sort of like non-logarithmic d dependence is shown here. In particular, there's no like lower order term. Other questions? Is that it? Okay, so in the last like 10 minutes, I'm going to try to maybe show quickly how we can actually apply this to RL and what this sort of buys us. Okay, so I'm going to introduce our algorithm now. Again, it's called FORCE, first order regret minimization via Ketone estimation. And basically it works by, again, going back to Akshay's question, we're going to estimate sort of these variance parameters. We'll denote by this V bar. We actually use a Ketone estimator to estimate that as well, but it's not sort of super critical at the moment. But basically, it sort of estimates the expected value squared of the next state value function. Then we'll form our lambda matrix, which is again sort of this the phi vector we've observed so far normalized by this variance dependence. And then we'll estimate the next state expectation using Ketone. And I'll show you in the next slide precisely what that looks like. And then we're going to compute a linear summary, as I just said. So now you compute some use the Ketone estimates to compute some WHK vector. Now this is sort of the approximation to our Q value function. And then we'll actually set sort of our optimistic Q value function of Q of HK will simply be this WHK, this inner product WHK times phi plus some bonus term. And this bonus is scaling critically with the variance normalized lambda. And then the algorithm is simply to take action AHK, which is just sort of the argmax of this Q function. And so in a sense, this is very similar, if you're familiar with Chi's algorithm, this is very similar to what Chi does. The main difference is here we replace his standard least squares estimator with a Ketone estimator, and we have to add the extra step of computing this variance parameter. But otherwise, it's a pretty standard UCB style algorithm. And so the estimate of the next state expectation given by this E hat, we apply the Ketone estimator to the data V transpose lambda to the -1 phi V h plus 1 k divided by this variance term. And so this is sort of essentially computing the next state, the expectation of VH plus 1, given that you're sort of in state S and action and taking action A at step H. And one can show then using our Ketone estimate that this expectation approximates to true expectation well up to, you have again some descaling, and you also get sort of a lambda scaling where lambda is a normalization factor. But then you get this scaling in terms of this variance dependent covariance. Again, we also compute the variance parameter using a Ketone estimator, and you can show that it is also an accurate estimate up to some lower order terms. And so intuitively, what's going on here is going back to this intuition I started with of you basically want to make your bonuses to scale in terms of the reward. We do that here essentially. So the bonuses are scaling with this variance term. And so if this is small, if the next state value function is small, we're going to give like a smaller bonus essentially, which induces less exploration and allows us to sort of like ultimately obtain the first order regret. So one thing I'll mention here is it's not actually clear. So computing this linear approximation, it's not actually clear how to solve this, right? So we're doing this complicated thing where we're sort of taking the min over W and the sup over all possible directions. But every possible direction, you're going to have to compute a Ketone estimate for. So you can imagine doing something where like you cover the sphere and you compute sort of exponentially many Ketone estimates, and then you solve that. You solve this in that way, but that's obviously not practical. And so to come up with sort of a practical way of doing this, what you can do is we can essentially compute the Ketone estimates only for the eigenvectors of lambda hk, and then you can show that rather than solving this problem to find the linear approximation, you can just sort of compute it in closed form by using these d-Ketone estimates. And this can be computed efficiently. It just involves an eigendecomposition. I should also mention Ketone can be computed efficiently as well. So all of this can be computed efficiently in like poly D sample or computational steps. The one issue with this is that you pick up an extra factor of D in the approximation error for for sort of this linear representation. So that's why I sort of mentioned at the beginning, we get this computation, our computationally efficient version scales a square root of D factor worse. And that's essentially why we lose a factor of D when we come up with this linear approximation in this computationally efficient manner. Okay, so I think I have a few minutes left, so I'm going to quickly then sketch out the regret bound, and then I will close for final questions. So it's pretty straightforward to show using this that optimism holds. So we can upper bound the regret using sort of the standard optimistic thing. We upper bound v1 star by v1k, our sort of the estimate of the value function that our algorithm obtained. And then using a regret decomposition that originally is due to chi, we can upper bound all of this, and I'm sort of hiding some lower order terms here, but the key thing is we can upper bound it in terms of just the optimistic bonuses we gave. And in particular, what we're going to end up doing is we're going to write these optimistic bonuses like this, and so we're going to divide phi by these v bar, because now you'll see that you have sort of a match between phi divided by v bar is exactly the sort of vectors that appeared in this lambda. And so we can apply something like the elliptic potential lemma here. And so in fact, that would be sort of the standard analysis. What you would do is you would apply Cauchy-Schwarz. If you apply Cauchy-Schwarz to this, you pull this factor apart from this factor. You're going to get the variance dependence here in this term, and then you have this sort of second term. And now the standard approach is you apply the elliptic potential lemma to control the second term. I don't think I have time right now to sort of state it. So if you're familiar with it, great. If not, just know that it shows that the second term would be summable. But there's actually an issue here. And the issue is that to apply the elliptic potential lemma, you actually need to choose lambda, the normalization factor, to be at least as large as the maximum norm of this vector here. And this is a problem because this actually is exactly the issue we ran into before with Bernstein, where you're going to end up with this scaling now in terms of this like minimum variance term. And so this isn't great. So we can't actually just apply elliptic potential here. So we have to do something slightly different. And what we do is we show the following lemma. So this is actually originally as a lemma in Chaba's, or as an exercise in Chaba's book. But it's a kind of cute lemma. And basically you can say that the number of times that this term, this sort of self-normalized term, will be greater than 1 is at most d log k. And so what you can do then is going back to sort of the regret upper bound we had, we can upper bound the number of times this is large, and we can replace this here with this sum here, where you now are just taking the min of the bonus and 1 rather than the bonus and h over v min. And because it was only large sort of d log k times, we just pick up this extra d log k factor. So now we can actually just apply the Cauchy-Schwarz and the elliptic potential lemma. So if we apply Cauchy-Schwarz, we can write this in terms of sort of the sum of the variances and this term that looks like the elliptic potential lemma term. And now we can apply elliptic potential lemma directly to show that this term scales as dh. And this ultimately gives us a dominant term in there where we're at scaling as beta, which is sort of just like this confidence bound times dh times the sum of these like variance terms. And you can show then, using some extra manipulations, that this term here can be upper bounded as h squared v1 star times k. And then beta is actually just equal to approximately d, so you get this poly dh v1 star times k. So to summarize, I know that was kind of quick. I think the key trick here again, applying katoni to reduce the dependence on the sort of magnitude of the noise, and then applying this sort of like elliptic potential, this sort of elliptic potential count lemma to sort of handle the fact, to allow you to choose lambda, the normalization factor, to be small. And if you combine both of these tricks, then what you'll end up with is sort of what we have here. This is v1 star regret bound. Okay, so I'm gonna close here and take any additional questions. Here are some references. But yeah, thank you all for listening.
All right, very nice. Thank you. Awesome. So I think there should be many questions. At least I have many questions. So maybe I can start. So here in this whole Ketone Estimator construction, you used the version that scales with the variance, right? That needs you to find the root of this phi.
Yeah.
So I'm just wondering, because you can get a simpler estimator if you're ready to accept a dependence, not on the variance, but on the second moment. Would that be sufficient?
So we kind of actually do, the dependence we do is more on the second moment. It's not actually a true, I didn't actually mention this because it's a kind of subtle technical thing. But what we end up using is we don't actually estimate the variance directly. We estimate, it's actually more of a second moment estimate. So we estimate just sort of the square of the value function rather than the variance of the value function.
Right, because then I feel that you could have done something simpler, because there is like a simpler version of vector valued katoni, which says that, okay, I'm just going to look at my random vector, and then I'm going to apply this Ketone estimator to the norm of this vector.
Yeah, we thought about using these. They didn't give us like sort of, at least the vector, maybe there's vector value katonis I'm not familiar with that you're describing, but the ones I've seen, they typically give the concentration not, because we really actually do need this very fine-grained concentration in terms of like the directions in some sense, or like the actual assays we're taking. Whereas these vector value katonis that I've seen are giving you just simply concentration on like the norm of the vector. And we really want it on like the actual directions. So we thought about that. It wasn't quite like fine-grained enough a Ketone estimate for us.
Yeah, that's my feeling as well. That would not be enough. And then instead of this covering, did you try to do something fancier, like Laplace's method?
We did not try to do Laplace's method. I don't know. I'd have to think more about whether or not something like that would work. I suspect it seems like Laplace's method, at least in terms of like how it's used to prove the self-normalized inequality, is like pretty specific to like the style of estimator you're using there in terms of just like a least squares estimator, whereas Ketone has like a totally different structure in terms of the estimator. So I'm not sure it would work, but I would need to think more about that. That is an interesting idea. Yeah. But even if that did work, like it wouldn't improve the dependence at all.
Right.
We'd still get the same like dependence that we have with Ketone. So, yeah.
Yeah, right. I'm just wondering about the complexity of this step that you're calling here, compute linear summary.
Yeah. So
Take
again,
the supremum over V.
Again, this is not computationally efficient, and so obtaining the computationally efficient version. Again, so instead of computing this is that sort of step you just mentioned, which is a supremum and this. You can just compute the following, which effectively does the same thing, but your approximation. This is saying essentially approximate it well in every single direction, where this is saying just like approximate it well in terms of the eigendirections. And it turns out this is sufficient, but you do lose a factor of d. So sort of obtaining like the same thing, but without losing that factor of d in a computationally efficient manner, that's I think still an open question and would be interesting to nail down a bit more.
Yeah, right. So here it would be nicer if it would be possible to do some post-processing with the least squares estimator, or just truncate.
Yeah, I'm not sure if that would be possible or not. It would be, yeah. but if that was, that would be really cute. That would be nice.
Okay, so then I guess I still have questions regarding all these like different flavors of this first order band. Okay, so maybe my first question that is still not that would be, so does this give you a second order band actually? Does it give you a band that actually depends on the square of the value function?
I mean, so what we actually end up doing, in some sense, yes.
V square.
What we actually show is like this V bar, which so our regret scales as V bar, and V bar is scaling as like the square of the optimistic value function. What we end up doing is we know like the value function is always bounded by h, and so we just upper bound this by h times like the just expectation of the value function. But you could probably derive actually something that depends on like the square of the value function and get like a second order style regret bound. So that we didn't actually think about that, but that would be an interesting, I guess, sort of extension perhaps of our work.
Right. So this is what brings me back to this first order bound with respect to losses, right? So if you have a second order bound that would have the variance here rather than the second moment, then you can get a bound that is small both when the best policy has small reward as yours, right? Or it's also small whenever the best policy has large reward, so like close to h.
Right. Yeah, so actually there is a subtle difficulty here with getting the variance dependent. So the reason we use a second moment is because, rather than the variance, is because the Martingale-Ketone estimator we sort of use has this term in the estimation error, which seems to be real, that depends on sort of the deviation, essentially like the deviation of sort of the like conditional expectations from the like total mean. And it turns out that the sort of end result of that is that you actually need to use, rather than the variance here, you need to use the second moment. So this is also why we actually can't, so you might hope like, oh, you're getting this sum of variances, and then you can just apply law of total variance and actually just reduce a factor of h in the worst case. We can't actually do that because you have to sort of use a second moment instead of the variance. So that removing that is an open question. I don't know if you can do it with Ketone or not, because again, this Martingale-Ketone has this term, which I think is real. So in answer to your question, that would be really cool. That would be an interesting direction for future work. Get it to depend on truly the variance. But it's not clear that Ketone, you might need additional tools or additional tricks to what we currently have.
Right. So if I wanted to, okay, let's say work with losses instead of rewards, right? Then get first order that depends. That is good when you get small losses.
Right.
Does this argument work there? I feel that no, this would not be enough. There you would really need to have variance dependent.
Right.
thing in there.
Let me think.
Because here, if you just accidentally pick up like a few big values, right, in this reward setting, that does not hurt your bound, right?
Mm-hmm.
Getting big rewards can only, make the bound better. But in the loss setting, if you have like a few big variances, a few big like L squares,
Mm-hmm.
then that can really hurt.
Right.
Yeah, I guess the root of all of this is somehow the shift dependence of these estimators.
Right. Yeah, I need to think more about the loss thing. And yeah, it's not clear to me that it will go through directly.
Yeah, and I suppose all of this is because that this martingale katoni, that is actually not really the katoni estimator that you were showing, because that one is based on root finding, the one that you showed at the beginning.
Yeah, so
That's an
actually
M estimator, right?
the martingale-katoni is actually the exact same estimator. The estimator doesn't change, just the analysis changes slightly.
Really? Okay.
So you can apply the exact same estimator. The analysis is due to Chen Wei. I believe he had a paper using this for contextual variance in 2020. That's what the martingale-katoni we apply is from. So you can go check that paper for the analysis. But it's the same estimator. It's just a different analysis to get the bound.
Okay, because the one that I'm familiar with, it's actually like very simple. It's on the first page of Katoni's paper. It says that you can just take this link function, this psi, and just push all of your x's through it, right? You just take 1 over alpha times psi times alpha xt. That already gives you this bound with the second moment instead of the variance.
Oh, okay.
So you don't need to do this shifting and root finding.
I see. Interesting. Yeah, I'm not actually familiar with that one.
And it works for martingales.
Okay. Yeah, so maybe that's something that could be done instead of using the one that we use from Wei et al. That is interesting, though. I'll look at that.
Sweet. So maybe some other people have questions, huh?
Yeah, I haven't been monitoring the chat, so if there are questions in there, maybe I can take a quick look.
Yeah, Akshay. Are you still here? He's a busy man. Oh no, Akshay is not over here.
I sort of had the same question as that, so it would be interesting to hear the answer.
Yeah.
In terms of whether you can replace it with median of means or any other robust estimators.
Right. So medians of means doesn't work, or doesn't seem to work. The issue is it doesn't seem that you can actually do a martingale median of means. The issue being that if you apply sort of median of means, it really depends. So median of means works obviously by sort of you block up your data into a bunch of smaller blocks, you take the means, and you take the median. But it really critically relies on the fact that all of the smaller blocks like have the same expected mean. And as soon as you go to a martingale setting, you kind of like lose that structure now because your data is sort of like moving with time. So I don't think median of means, to my knowledge, median of means can't be applied in this problem due to that. That is the main issue with median of means that we ran into. We did think about applying it though. But Ketone obviously has this sort of martingale version that you can apply.
Cool. Makes sense.
And then it looks like Ranshi has a question. In the computationally efficient method, can we get similar performance by calculating WH using just the principal of eigenvector, the one with max eigenvalue? I think you need to calculate it for all of them because you basically do need to guarantee in some sense that your approximation is accurate in every direction. And so if you just did it in terms of like a single direction, you wouldn't necessarily have that. But if you sort of compute it in every direction, or the sort of all of the eigenvectors, you can sort of show that it, yeah, it's like accurate in every direction up to some approximation error. Any additional questions? Chaba.
Right. So the first question I have, whether you have a control of the tail of the regret, because these estimators, they work with a fixed confidence. I suppose you're gonna set a confidence to be inverse polynomial, so the data is going to be like 1/k or something like that. K being the number of episodes in your regret bound, and then you can control the expected regret, but
Yes.
you want to get a high probability regret bound that shows the nice scaling with everything.
Yeah.
Then,
So is your question how to get, or what the expected regret bound would? So the one we sort of proved is a high probability regret bound.
yeah, but it's not really. It's just like, because the algorithm takes as input data. So a super bond would be that you have an algorithm that's independent of your data. You take a, like, whatever, like you can take a data, but then you want to prove that for every data is in a reasonable,
Yeah. So this is
the regret is controlled.
right. So yeah, you're correct, and then it takes as input a delta, and it uses a delta in, again, the Ketone estimates. So in some sense, it does just hold for a single delta.
Right.
So it wouldn't give this necessarily this like uniform style.
Yeah.
Andrew, do you mind if I chime in on this question?
Yeah, go for it, Max.
Yeah, I feel like this is a problem in really all the provable RL algorithms, right? Even if you think about like, what is it, LS, or sorry, UCBVI from like Azar et al., Azar and Osband, these also take a delta as input, and it's not even clear how these algorithms have a controlled tail otherwise. Because once the confidence bounds and the value function go wrong, you don't really know what's happening. So even with much simpler algorithms, this is going to be an issue.
Well, I guess
even in UCB, it's potentially an issue.
I don't really know that, because if I'm just thinking about bandits, like you could also say that, oh, for bandits this must be a problem, but it's actually not a problem, because you choose a data which is this inverse polynomial, and then you can prove that the regret is still controlled with high probability, like in, it's so the argument, like I understand it, but I'm not sure I completely buy it. It's true that it's not been worked out in a lot of other cases, but what I'm saying, I think, is that for the tabular setting, maybe there is absolutely no problem, but here there is a difference, because, well, I don't know whether there is a difference, but like it feels like that this data plays a more crucial role in even how you're computing it, because normally you just go with the empirical mean, you're happy, and like the empirical estimate under the nice sub-Gaussian setting is gonna have like control tail behavior. And there's no problem with that. And the algorithms are inheriting this. So the regret is many times nicely controlled. Although there are phenomena that you're trying to make things more aggressive, and then suddenly you're not controlling the tail of the regret. So there is actually already for finite time bandits something going on there.
I mean, I guess
not in every case, but
if I had to conjecture, I would imagine that you'd probably have to start with and I think you've done a lot of work in this space, is using sort of randomized rewards or sort of fake rewards, and using those to enforce exploration rather than confidence intervals. Then you could probably prove
some smoothing kind of
thing.
But I don't know whether like whether the katoni estimator, these robust estimators, they're gonna prevent you from doing this. But yeah, with the current analysis, it's kind of hard to do it, I guess. That's for sure. But yeah, I'm really interested in whether this is a fundamental limitation of going like about solving this problem this way, or is it just the analysis is going to be much more complicated and the algorithm could remain the same, and then the regret is fine? Like the concentration of the regret is still fine.
Right, you're talking about sort of if you were to apply sort of an algorithm without using Ketone?
Well, that was Max's idea.
Yeah.
Oh, I'm just saying, like, I mean, all I was saying is like, yeah, even in tabular RL, the way to get around this fixed delta thing would probably have to be some algorithm that uses randomized things. Maybe what you could do is you could use Ketone on some randomized thing and use the randomization to replace the delta dependence. But that's probably going to derail the conversation here. But I would imagine you need to do something like this.
Right. Okay, so some more work to be done. Regarding the discussion at the beginning that we had about costs and rewards, though we have seen the algorithm, if I look at the algorithm, it doesn't strike me as like you couldn't apply the whole thing for if you have costs. You have to.
Yeah, I mean, I think, okay, I guess I'll say like, I think
lower bounds and like,
I think probably if, right, the structure of the algorithm, as I said, is basically like cheese algorithm or pretty much any of these UCB algorithms. So I do think as long as you could push it through in those cases, it probably would work here.
But then would that address Gary's question about the first order bounds with losses? So now we are switching to costs. So we want to minimize costs. Costs are non-negative. They get really small for the optimal algorithm. Then like you are demanding a lot of this algorithm, but you can flip around things, right? So instead of upper bounds, you compute lower bounds. And then other than that,
Can I chime in again on this, Andrew?
Yeah, go for it, Max.
I feel like, so the thing that shows up in the analysis is we need to pay for sort of the variance of the conditional expectations. So for example, a total variance might not work, but you probably could show something where like, if all the rewards are very large, then then you would be able to get the same thing. So the thing that kind of kills us is like, it's the variance of the conditional expectations that kills you, but potentially if all those things are very big, you might be able to flip losses and rewards and get something similar. We could look through that.
Okay.
Yeah.
All right. That would be interesting. Cool.
Yeah, I guess I can just only repeat myself, but I think that you would need to replace these second moments with the variances to get first amounts for small losses.
Why?
Yeah, because so as I said before, somehow here, if you just accidentally pick up a few big rewards, that doesn't really hurt you. Like it shows up in the second moment, but it's fine. It's the right order, or like smaller than what you get from the best policy. Whereas if you do this for losses, then you can get like a few big terms in your regret, and that can hurt.
Oh, you mean that like, okay, you start with a bad policy, it has a lot of loss. Now your confidence intervals are really wide, and you're gonna learn very slowly because of that, and somehow this boosting doesn't really happen. It's like maybe you have to do something with the algorithm too. I see. Because with the rewards, what happens is that, yeah, if you're not picking an optimal policy, you pick a bad policy, your confidence intervals is just narrower. It's great. You're learning really fast. It really helps you.
Could you, I haven't thought too much about losses, but would something just like even flipping the So you get a loss of something. Now you just set your reward to 1 minus the loss. It kind of like does the right thing in a sense, right? And I think in that case, you would actually maybe get the right scaling. I'm not sure if that would go through, if you could push that through the full way, but because essentially I think what you're saying, Gurley, is like if you just directly apply this to losses, like now you're going to overexplore sort of the bad loss parts. But like you just have to sort of like tune your exploration bonus and that sort of like logics out sort of what a loss or reward is. And so if you just sort of like made your bonus to scale with like 1 minus the loss, it might do the right thing in the end.
Yeah, so somehow in my experience, like tackling this small loss setting is a lot harder, really, because there, if there is a policy that gets you like a near zero loss, right, or like in the ideal case 0 loss, then it should work amazingly well, right? Then you can only have like logarithmic regret, like even for like whatever small gaps, and somehow this looks like impossible to get from this bound that you currently have, right? It says that if the optimal policy has like a huge reward, right, this just increases your bound.
Yeah. So the 1 minus, so reacting to that. So if the loss is there for the optimal policy as 0, then in the 1 minus you get all ones, which makes it very generous for your bound. But we didn't want to be generous. Like in the bound, you don't want to flip the loss to the 1 minus.
Sure. Right.
Yeah. So it seems like that. Yeah, it's kind of tricky. That's a cool problem.
And with this, I'm not saying that it's easy to get bounds for first order bounds for rewards. I'm just saying that for losses, it's a lot tricky.
Right. Yeah. I'll think about this. I'll think about this some more and maybe follow up with you via email if you're curious. Yeah.
Yeah, that sounds good. I'm curious as well.
Okay. All right. Cool. Well, I feel I learned a lot.
Yes, this is very cool. Very cool.
I knew that these robust estimators are coming. It was unavoidable. Big conversions. Yeah.
All right, folks. So I guess I'm going to be going home.
Yeah.
Getting a bit late.
Thank you.
Over here. Thank you very much, Andrew.
Thanks a lot, Andrew.
Yeah, thank you for the invitation.
Yeah.
It was a really nice talk.
Yes, and thanks everybody for coming back. And
See you next
coming
week.
back for more.
Yeah.
Next week. I'll see you more regularly now.
Bye.
Bye-bye.
Thank you. Bye-bye.